Week 8 in statistics. Hey, it's me, Gary Parker. Central limit theorem is the big idea. We've been working on that for a couple of weeks, and now we dig into some formulas that predict the center and spread, right? Center and spread of a distribution of sample means, of a distribution of sample proportions. We're going to look at means right now. So I have some data on river temperature. So we took a bunch of samples in a region of a river in the spring. Now, past experience, we expected the average temperature around this time to be 10.5 degrees Celsius. However, looking at the sample, we are thinking that it might be a little bigger. Well, clearly it is bigger, 12.5. The question is 12.5 a lot bigger for a sample like this? Or is it just a little bigger and not a big deal? And that's what a hypothesis test helps us answer. Is it a lot different, or is it not really much different? Because bottom line is, anytime you do some kind of sample, the result's going to be a little different due to just variation in reality. So here I have a spreadsheet set up. And again, my null hypothesis is that I'm expecting the river temperature to be about 10.5 degrees Celsius. A null hypothesis has an equal to statement. So it can be equal to, less than or equal to, or greater than or equal to. Those are the three options for a null hypothesis comparison between a population parameter and the actual value. Alternative hypothesis is not going to have an equals. So it could be greater than, could be not equal, or it could be less than. In this case, I'm thinking greater than, and my hunch is based on the sample data. And clearly the sample mean, X bar, is bigger than what I expected the population mean to be. For this particular sample in column A, the standard deviation is 2.82. I'm going to go with the standard 5% significance level to test whether this is a significant difference from what was expected. Standard error. So this is the big idea this week, that the central limit theorem says we can predict what the standard deviation of a sampling distribution is going to be. And for a mean, what you're going to find is that it is the population or sample standard deviation, S, divided by the square root of the sample size. Now, ideally, we'd like the population standard deviation, but we usually don't know that, so we approximate it with the sample standard deviation. Because of that extra bit of unknownness, right? We don't know the mean exactly. We think we know what it is. We don't know the standard deviation, but we have an estimate for it. Instead of using a normal distribution, we're going to use a t distribution here. And that means we're going to calculate what's called a t statistic. And then we're going to predict a p-value, calculate a p-value by using this t test statistic and the t distribution. So the test statistic is always of this form right here. And what this form is, kind of in more plain language, is you take whatever your sample statistic is, and you subtract whatever the null value is. And then you divide that by the standard error. And I'm writing it in more general terms here because what we call this number, the sample statistic, what we call that, the null value, and what we call the standard error is going to vary depending on whether we're talking about a mean or a proportion. And then next week, whether we're comparing two means or comparing two proportions. So the formula is going to vary a little bit in the green context here, but it's always the same way in the red. Sample minus null over the standard error. This is what we call a test statistic. So in this case, looking at the randomization distribution here, I ran in stack key, and you can see I overlaid the t distribution on top of that. They match up pretty nice there. Given a sample mean of 12.495, we're expecting population mean of 10.5. And again, anytime we do a sample, we're going to get variation because we don't have the whole population. A sample could be over here, could be over there, could be over there, could be over there. The question is, if I have a good random sample, is my particular sample too far from the middle to not be explained by just random chance? I get a t-score, which is like a z-score, of 3.42. That means my sample is 3.24, excuse me, 3.24, not 3.42. My sample data for a size of, if this was 21 samples, is 3.24 standard deviations from average. If we think about the 95% rule, that means we expect that just due to random chance that we're going to find a value that's within 2 standard deviations. This particular sample has a mean that's more than 3 standard deviations from what's expected given this sample size. Sample size matters. Hopefully you remember that from the last chapter. Let's look back at the spreadsheet here. Now, before we were running these randomization distributions, which are awesome and powerful and great. And again, we're comparing that to what the central limit theorem predicts. So that's like we flip a coin 100 times, we might get 48 heads, but we expect to get half of them heads, 50 heads, right? But it's always going to be a little bit different. Sometimes we'll hit 50 heads out of 100, sometimes we won't. So we have randomizations versus theory, and they should come close for bigger sample sizes. Is 21 big enough? The answer is we'd like 30 or more, but sometimes we're stuck with small samples and we have to make do. And again, a t-distribution helps us deal with that extra uncertainty from having a smaller sample size. The theoretical t-distribution, which I calculate with this formula here, t-dist, and I'm using the right tail version. And I enter my t-score, that's the test statistic. And a t-distribution only needs what's called the degrees of freedom, which is always the sample size minus 1. And so that's what I have next there, and minus 1. And so here I get a p-value of 0.002. The randomization distribution got a p-value of 0.0005. Notice they're not quite the same, but I would say they're in the ballpark of each other. They're both pretty darn small. What either one of them tell us is that's a wicked small chance of having a sample mean that high with a sample size of 21 when we thought the mean was going to be 10.5. So something weird's going on here. So we question, maybe 10.5 isn't the right mean anymore, or I just have a weird sample. In these situations, we usually say, well, no, we have a good sample. We did a good job selecting the sample, so the problem must be with the null hypothesis. So this particular sample is evidence that the alternative hypothesis is correct. And do we know it's correct? The answer is no, we don't. There's always this room for an error. And p-value talks about that error just a little bit. There's a 0.00057% chance of finding another sample with a higher mean than ours when we thought the mean was going to be 10.5 with a sample size of 21. So decision, reject the null hypothesis. Conclusion, we have to think about the situation again. So we're looking at river temperatures here in degrees Celsius. We're expecting the river temperature to be 10.5. So we have significant evidence. It's a right tail test, right? We have significant evidence that the average river temperature is higher than 10.5 degrees Celsius. Now, we can't go out and tell everybody, hey, average river temperature is now 12.5. We don't know that for sure. We'd have to run a confidence interval to get a predicted range of values for the new population mean, but we have evidence that it's bigger than 10.5. Hope that was helpful. Take care, do good math. I'll see you soon.